I'm recording.
Okay, so I guess maybe there's one more to come. We've got 4, 8, 9. Who's missing? Oh, okay. Well, anyway, we'll go ahead and get started. So you have the rare privilege of an entire day with me, but I promise not to talk the whole time. So this is all about learning how to run this Hydrolight software. So how many people have already run Hydrolight wherever you come from? So there's a couple. How many have heard of Hydrolight but never run it? So a couple more. And how many have never heard of it till you got to this class? Okay, one. Well, that's almost exactly what yesterday's numbers were like. And then how many people have mosquitoes as bad as they are here, wherever you came from? Okay, because we walk up the road, it's not bad down here, but boy, walk up the road to the cabin and you'll get like 20 mosquito bites in 10 minutes. It's really grim. So anyway, so what we're going to do today is I'll start out, give you a little explanation of what Hydrolight and Ecolite are and are not, and that'll take us, 30 or 40 minutes. And then I'll do some demo runs to show you how to do little simple simulations like of case one water. Then I'll give you some sort of homework problems. You guys can start doing simulations of your own and just do that for the rest of the morning. I'll sit in the back of the room and watch funny cat videos. And then this afternoon, I'll give you and I'll also, show you how to look at the output. Then this afternoon, I'll demo a couple of more complex things like how to read in your own AC9 data, et cetera, and how to build up case two waters. And then there'll be another batch of problems that you can work on. And yesterday, some people worked through all of those problems. Some people have already done 10,000 Hydrolight runs before they got here, so they just went off and started doing other things. And then for your presentations tomorrow, get together with yesterday's class. And I don't have any real plan for how you present things. There's a dozen different simulations here. You can just put a view graph on, the first simulation we learned this, or here's what came out, and just kind of figure out what you think is worth discussing there. And I think that'll kind of become obvious as time, as you work on the problems. Okay, so anyway, let's roll then. As I think I've already done that, we're going to go over it. And then same thing in the afternoon. And then, of course, for the rest of the course, you can play with Hydrolight, use it in your projects or not, as you prefer. Okay, so first of all, with any model of any kind, whether it's Hydrolight or anything else, there's some kind of physical model, which is basically what's the physical problem this thing is supposed to solve. And then there's a computational model. And so those can be much different. So we'll use a Monte Carlo code next week that solves the same physical model of solving the radiative transfer equation, but with entirely different computational approaches to it. So we'll talk about that kind of stuff. With Hydrolight, which is the original software, there's also a thing called Ecolite that comes with it. They both use exactly the same inputs. Where they have common outputs, they're the same, but Hydrolight gives you more output than Ecolite does, but it takes longer to run. And we'll see how that works. We'll talk about how the software is organized, and then away we'll go. And has everybody already installed Hydrolight and nothing horrible happened? So, okay, so yesterday it was really weird. We had two people with MacBooks. One of them works fine, Jeremy's works fine, and then one person gets to this one button on Hydrolight, and when she clicked on that button, the thing freezes up. And it's like, well, we've never seen that one before, but anyway, we'll find out those kind of bugs if there's any in here, because this is really sort of beta test code. Okay, so the physical problem we're solving here is, as I mentioned the other day, if you want to solve the radiative transfer equation, what you have to have is some region where you're interested in solving it, and you have to know the IOPs in that region. And then you have to know the radiance incident onto that region and whatever boundary conditions for reflectances or whatever there are at the boundary. So in general, that gives you a three-dimensional problem. You could think of computing the light field in a cloud, for example. Well, what happens in Hydrolight is we just take this region of interest, stretch it out horizontally, and make a horizontally infinite ocean, which is the same in all horizontal positions, but things can still vary with depth. The bottom can be infinitely deep, it can be finite depth, and you can say the bottom reflectance is for sand or seagrass or whatever. And then we have a one-dimensional problem, which allows certain mathematical techniques to be used, which make the solution much, much faster than if you have a three-dimensional problem. And so today, Hydrolight's a 1D problem. Monday we'll talk about Monte Carlo and have a lab there, and Monte Carlo can handle three-dimensional problems, but at, thousands of times slower sometimes. Okay, so our friend, the radiative transfer equation, we've seen before, and what's going to happen in Hydrolight is you have to put in the IOPs, absorption, scattering, phase function, and if there's an internal source like bioluminescence, you would have to specify that. You have to tell it the light that's incident onto the sea surface and the waves on the surface and so forth, and that fixes up the boundary conditions. And then Hydrolight solves this equation for the radiance here. And then all the irradiances, reflectances, K functions, all of those things are computed using their definitions and using the radiance that Hydrolight solves for. So to get ED, it just takes the solution radiance, integrates it over the hemisphere, etc. Okay, so notice first of all, what goes into the equation here is total absorption, total scattering, total phase function. It's not how much is absorbed by water plus phytoplankton plus CDOM plus whatever. The light just cares about whether it got absorbed or it didn't, and it doesn't care whether it got absorbed by a phytoplankton or a water molecule. So kind of keep that in mind. And nothing in here says anything about pigments or particle size distribution or anything like that. Those things are all parameterized by the IOPs. So yeah, we may build up the absorption coefficient from different phytoplankton, CDOM, maybe you have a model that you run offline where you add all the different pigments together and build up a phytoplankton, and then that's the phytoplankton absorption, and then you can take that into Hydrolight and build up eventually the absorption coefficient. And there's nothing in here about index of refraction and size distribution, but those effects are all parameterized in the phase function. Okay, so I think we've already said that, and it's only oceanographers that care how much light's absorbed by phytoplankton versus CDOM. Okay, so in brief, we're going to put in IOPs, we're going to have boundary conditions at the surface and maybe at the bottom, and all that goes into the radiative transfer equation. You get out the radiance, and then everything is computed from the radiance, and that's all handled internally automatically by Hydrolight. So the physical model, it's time independent. Well, in radiative transfer theory, time dependent problems are when you're talking about something like a pulsed laser where the light field is changing on a scale of nanoseconds. Here, you can solve a time-dependent problem of, let's say, the light distribution over the course of the day, but what you do is you run Hydrolight at 9 in the morning, 10 in the morning, 11 in the morning, and those are all time-independent problems, and then you can add all that together and get the solution for the day. As I said, one spatial dimension. The code that you have runs from 300 to 1,000 nanometers. That's the limits. There's nothing in the math that says you can't run at 280 nanometers. The problem is that the databases that are in Hydrolight only go between 300 and 1,000. So if you want to run Hydrolight at 280 nanometers, well, that's fine. Just give me what does phytoplankton absorption, CDOM absorption, mineral absorbing and scattering, etc., bottom reflectances look like at 280, and then you can just add those to the database and away you go. But the problem is nobody ever measures things like seagrass reflectance at 280 nanometers. So if you want something to do when you get home, extend the database. Then there's, in the full code, there's 3 different ways of modeling the sea surface. The only one we'll use in here is this Cox-Monk model, which Jeremy Wardell mentioned that's how they do their atmospheric correction stuff when they model surface reflectance. It's with these very simple equations that go all the way back to 1954, but those equations capture what you need to do a decent job of modeling the sea surface. And we'll have a lecture next week on how some of that works. So there's various bottom options. You can let the water be infinitely deep, you can let it be finite, you can then put on whatever reflectance you want if it's finite depth. Hydrolight includes all orders of multiple scattering. Now, we talked very briefly about this successive order of scattering approximation in the radiative transfer lecture, where you write the total radiance is what's unscattered plus scattered once plus scattered twice, and then maybe you drop all the terms of 2 or more scatterings and you get an approximate solution. Well, Hydrolight doesn't do that. It actually solves for that infinite sum using some kind of nasty mathematics, but that's how it works. You can include inelastic effects, Raman scatter by water, fluorescence by chlorophyll and CDOM. You can have internal sources like bioluminescence, but there has to be a horizontally homogeneous layer of bioluminescing things, which you do get in places like the Arabian Sea. You have this just vast sea of bioluminescing bacteria that you can see from space. Or, if you're sitting on a ship that's so bright you can read a newspaper sitting on the deck of a ship. So that's the sort of thing that's here, but not like a point source of bioluminescence or a light bulb in the water, because that's then a 3-dimensional problem. And it doesn't include white caps in the sea surface model. And then the main restriction is it doesn't include polarization. And I commented on the radiative transfer lecture that gives you sort of plus or minus 10% errors in the radiances, but that's the least of your problems, because you probably have much bigger errors in your IOPs going into it, and that's really the limiting thing. So then the computational model. Well, you really have a radiance distribution that's a continuous function of depth, direction, and wavelength. Any numerical model has to figure out some way to turn these continuous functions into a finite number of numbers that it can solve for. So what Hydrolight does is it takes the actual radiance distribution, and you can think of it integrating over little windows here, like little latitude, longitude partitioning of all directions. So there's little windows here. And so when Hydrolight says, here's the radiance at, theta equals 40 degrees and phi equals 50 degrees, it's really looking at a little window that's like 10 degrees in theta and 15 degrees in phi, and it's giving you the average radiance over that window. So there's the averaging over solid angle, and then you run it from, say, 400 to 700 nanometers by 10 nanometers. So the first band will be 400 to 410, and it'll call that 405 in the output. But what it really is an average over 400 to 410, where like the sky radiance distribution has been, it's in there in Hydrolight at 1 nanometer resolution, so it'll average the values over those 10 nanometers, and that's what you get back. And then it will save the output at a finite number of depths. So when we run the code, you'll tell it, I want the output saved at these depths. So you end up with some finite number of numbers that are these spatial and directional, spatial and wavelength averages of the actual continuous variable. So that's how the computational model works. And in Hydrolight, the x direction is downwind and the z direction is into the water. So theta equals 0 is light going straight down, and theta equals 180 will be radiance going straight up. So that's LU, for example. So it's always a little confusing when you look at the output. Like, oh, you know, the sun is actually at an angle of, say, 135 degrees. Well, that's really like 35 degrees from the zenith, but it's 135 there. So it can be a little confusing looking at the output, but anyway, you get used to it. Okay, just some quick comments here. The runtime is linearly proportional to the optical depth. So if I go to 20 meters depth, and then maybe that's 5 optical depths at a particular wavelength, and then I want to go to 40 meters, and that's 10 optical depths, it just takes twice as long to run. With Monte Carlo, you'll see Monday, the runtime builds up exponentially with optical depth. So people who run Monte Carlo codes, they don't go down to 100 meters depth. They're up in the near surface waters just because they don't have the computer time to compute the light field to 100 meters. You'll see how that works Monday. You can put in any profile of the IOPs. So, for example, here's depth, and here's A, B, whatever. You can put in, you know, this profile here, and Hydrolight's perfectly happy with that. There are other techniques, like one called discrete ordinance, where you have to approximate this as a bunch of homogeneous layers, and then each layer takes the same amount of computer time. So discrete ordinance, which is a numerical technique, if the water is homogeneous, it's very fast. If you have to have a lot of little homogeneous layers to approximate your IOP profile, then if there's 100 layers, it takes 100 times as long to run. But Hydrolight will just take whatever profile you give it and go with that. And it doesn't cost you any more computer time. Okay, so in one sense, it's nice because you get to specify all the inputs for Hydrolight. It doesn't assume anything about your water body. The downside is you have to specify all the inputs because it doesn't know anything about your water body. But on the other hand, for things you don't know, like say you didn't measure the volume scattering phase function, well, there's big libraries of things built in, and you can pick one of those values, or you can guess it, and you can use biooptical models if you don't know the absorption coefficient you didn't measure, but you measured the chlorophyll, so you can pick a biooptical model that will turn the chlorophyll into absorption and scattering coefficients. And then there's a graphical user interface, and really all it does is it collects all of your input, writes it off to a little ASCII file. It's like 30 lines long. It just has names of your files and chlorophyll concentrations and what depths you want the output at. And then at the end, it just spins off a command window and pipes that output file to the executable. So you don't actually have to run the front end. You can make those little files yourself and then just send them off to the executable. And the people that do, millions of runs, that's what they do. They don't sit down at the computer a million times. And then you can look at the output with printout, with Excel, with IDL plots and so forth. And we'll see how that works in a minute. So one of the main ways that people use Hydrolight is it gives you a controlled environment. When you go out to sea yesterday, you measured IOPs, you measured reflectances, etc., and you just had to take what was there that day. Now you get back and you say, well, gee, I wonder if, the absorption had been 30% greater, what would that have done to my light field? Or if I had had, more mineral particles in the water, if that would have changed the phase function, what would that have done to my light field? Well, you can't do that experiment in the field unless you want to wait around for those particular conditions. But with Hydrolight, you can do a run, you can change the absorption, do another run, see what difference it makes. So that's how it gets used a lot. And sometimes maybe you have an image of an underwater object that's made in the daylight, and if you run Hydrolight as though the object's not there, you get what that daylight field is like, and you can subtract that from what you measured, and get a better image of what it was that was in the water. So that tends to be what Navy people tend to do. So those are kind of the ways that it gets used. And in here, you know, you can play with Hydrolight, get some feeling for how light fields look in the water without having to spend 10 years doing radiative transfer theory. Okay, so just to reemphasize from the user's guide, and there's a user's guide that basically tells you here's how to install the code, run it, look at the output, and then there's a technical document that if you want to know, like, how does the new case 1 water work, or how does a sky model work, this has all the equations and shows you plots of the data and so forth. So there's a couple of copies of this floating around if you want to look at it, but I can tell you from experience, no one ever actually reads the documentation. If they did, that would cut the number of user support questions by like 90%. So anyway, as I said, Hydrolight doesn't know anything about your water bodies, so you have to put in all the IOPs one way or another, the boundary conditions, etc. And it's generally garbage in, garbage out. If you do something really stupid like put in negative absorptions, what it will usually do is it will put this rude error message in the output that says, you had a negative absorption at this depth and wavelength. I reset it to 0 and kept running, but you need to clean up your data and don't trust your output. So I either had that choice or to get to that point and say negative absorption, stop the run, this isn't physical. Well, I took the first choice. And you know, sometimes on an AC9, if you have an absorption profile versus wavelength, and you've done your scattering correction here, and maybe out here at 700, beyond 700, you might have slightly negative values, but that doesn't matter. On the other hand, if you have a negative value at 440, well, you've got a problem with your data. Okay, here's an example of an AC9 profile. Now, the AC9, I don't know about ACSs, but it samples, I think it's 6 hertz. So this profile is just lowering it through the water. It's getting a zillion data points here, 2,000, and there's some biology there, but there's a whole lot of instrument noise. Now, you can take that profile and give it to Hydrolight, and it's going to actually solve the radiative transfer equation for that exact profile. But that's not really a good physical problem. You need to take your data here and bend it or smooth it or do something to it and try to get rid of this random electronic noise and then just keep what's probably actually physical or biological information. So in this case, I took this profile, I bend it into 25 centimeter thick bends, and I got a profile here. That's what you want to feed into Hydrolight, not that one. So just kind of keep that in mind that Hydrolight can't clean up your data for you. You need to clean up your data, you do all your scattering corrections, you bend it, you smooth it, you throw out the bad values, whatever, and then you finally give that cleaned up good data to Hydrolight. Okay, in Ecolite, here's the idea. So with Hydrolight, you're solving for the radiance in each one of these little windows. And the runtime is proportional to the number of little windows squared. The reason is, well, when you're looking at light going into this window, it can scatter into all other windows, and then you go to the next window and it scatters into all other windows. So the math is the number of windows squared. But if you're going to compute ED, for example, you're taking all of that information and integrating over direction anyway. So you're throwing away this detailed information when you integrate over the upper or lower hemisphere of solid angles to get your radiances. So what Ecolite does is it solves an azimuthally averaged radiative transfer equation. So instead of giving you the average radiance in this little window here, it gives you the average radiance over this whole big band here from phi equals 0 around to 360. And still the same 10 10 degrees in theta. Well, now instead of having, let's say between the equator and the pole, we have 10 by 24 windows. Now we just have 10. So it's a factor of 24 squared that you save in runtime. It's not really quite that much because there's some fixed overhead, but that's the idea. So then, if you run Ecolite and compute the irradiances, you're summing up these averages and you get exactly the same irradiance as you do here. And you get the same polar cap radiance. So if that's all you want is like RRS or irradiances or KD or something, you can run Ecolite. If you really want to know the radiance in this direction versus this direction, then you have to run Hydrolight. That's the idea. So you can play with that. And they both take the same input. And so the way the code works, the core mathematics code for Hydrolight and Ecolite is written in Fortran 95, and I rewrote every line of the code last year. It probably took 5 or 6 months. There was over 30,000 lines of code in Hydrolight, and it's all mathematics, which you don't want to see. Although I'd be glad to teach a 1-month course to show you the math if, like, Jeremy can get NASA to shake the money loose, and I'm sure there would be at least 2 students in the class. So anyway, there's years of development here with me and this fellow Preisendorfer. But anyway, that's done. The front end, the user interface is C++, and then each one of these, the same source code gets compiled for either Windows, Linux, or Apple, and then pieced together to give you the Windows version, the Linux version, or the Apple version. And then sort of the bigger view, you've got some common databases up here used by both Hydrolight and Ecolite. You've got some common Fortran code, so like an IOP model is exactly the same for Hydrolight or Ecolite. And then there's the math-specific code for either Hydrolight or Ecolite, and those get compiled separately. Then in the user interface, you're going to run it, you're going to pick data files, you're going to maybe read in your own data, you'll use some that comes with Hydrolight, it'll create this input file, and then the same input file runs either Hydrolight or Ecolite, solves their respective versions of the radiative transfer equation, and then gives you output of either printout, Excel spreadsheets, or digital files. So that's kind of the way the whole thing is organized. Okay, the brief history is, back when I was a postdoc, I just happened to have an office next to this guy, Preisendorfer. Long story, but I ended up working with him, and we started, you know, he gave me this stack of equations like this thick and said, well, turn these into a computer program. So that's how it all got started. And I won't go through the details. I think in the library there's a PDF called Hydrolight History, so it kind of gives you the full horror story of my postdoc and so forth. But anyway, we worked on this code. It's entirely without any funding. We weren't supposed to be working on it. We were supposed to be doing other things. And so then we finally got it working about 1985, did like 3 runs, and then he fell over dead of a heart attack. And so nothing much got done with it. Then I started occasionally publishing a paper. Then people would say, oh, you know, I saw your paper, can I get a copy of the code? And I'd say, sure, here it is. And then they'd say, well, it would be nice if you had this feature. So I'd add that feature, and then pretty soon that got to be a kind of full-time job. So the typical story in oceanography is somebody develops an instrument like the LIST, for example, or the AC9 for their own purposes. Then other people want the instrument, and then they end up commercializing the instrument and saying, well, it just has to pay its own way now. So there's a company that will sell you an AC9, there's a company that will sell you a LIST. And the same thing happened with Hydrolight. When it kind of got to be more than I could do for free, I commercialized it in 97, I think it was, or 96, and became a product of the company where I was working, Sequoia Scientific, same guys that make the LIST. So, way it went. And then that gave me the funding to make new versions and do user support and all that kind of stuff. But there was never any government funding went into the development of the code. There's now well over 200 licensed users in 30-something countries, so it's pretty well accepted as like what everybody uses. Then a few years ago, when I was starting to think about retirement, I passed it on to this fellow, John Headley, who has a company, Numerical Optics Limited, in the United Kingdom. So it's now his code, it's his company. I'm completely out of the picture for, anything there. Sequoia is still the U.S. distributor, but you can also just order straight from Headley. So anyway, that's the brief story here. So Headley has put together this sort of student version that's about 99% of the next version. And you're sort of like the last beta testers before we turn this loose on the public, or he turns it loose. The code you have will run 500 times or until the end of this month. So feel free to use it. And then on July the 1st, when you run it, it will erase your hard drive and sends a message off to the CIA that you're actually, a Russian spy or something, and you should not ever be allowed to fly again. So anyway, that's the story there. And I brought the Windows, he sent the Windows and Apple versions here because we don't usually have anybody with a Linux laptop. Okay, so that's the story. We of course have to have a pretty picture. Can't get by without that. So at the one of the times I was rafting the Grand Canyon, so I'm down by the river. Here you can see the canyon wall. And so I set my camera up, I opened the shutter, I held the shutter open with a rubber band and pointed it at the North Star and then went to bed and just let it go till the battery ran down. Well, here's what you see. So when you go outside at night and you look at the stars, they all look pretty much white. Well, that's because the rods in your eyes that are what get used for low light conditions only work for black and white. The cones that you use in the daytime can see color, but they're not as sensitive. So all those stars that look white, if you actually look at them, they come in all colors. So, there's some white ones, there's red ones here, there's very dark red ones, there's kind of orangish ones, there's very pretty blue stars, etc. So stars really come in all colors, and that depends on the temperature of the star and the corresponding black body radiation curve. So here's the question now. If you pick some little corner of the sky where if you looked at it in a telescope, there's no stars, there's no galaxies, there's just dark sky. There's still some light there. And that light comes from starlight that's getting scattered by interstellar dust and interstellar gases, and some of it happens to go in your direction. So the astronomers, if they're looking at, let's say, a galaxy, they take this background sky spectrum, they subtract it out of what they measure, and then what's left would be the spectrum of the galaxy. So here's the question now. If you pick this darkest little patch of sky, if it were bright enough to see the color, what would be the color of that background skylight? Assuming you didn't ask this in this class, who already knows the answer. So I had a paper one time where I was a co-author, and it was a bioluminescence study. It was being done at night, and the guy said, and we subtract the background skylight distribution thing because we still have starlight on the ocean, and we're getting rid of that so we can look at the bioluminescence. And I read the paper and I said, well, that can't be right. The average color of that light must be white because there's all these white stars up there, and they're more or less like the sun. So it's just reflecting that light, and it ought to be kind of a neutral white spectrum, sort of like sunlight. It's not. Yeah.
Is it kind of like the sky where you see the blue because the size of the particles that are
Reasonably good guess, totally wrong. It's actually pumpkin colored. It's kind of like almost the color of this little podium. I don't see anybody appropriately dressed, but Yeah, it's more red than that. But anyway, it's a very reddish spectrum. And I said, well, that just can't be right. But then I read up on it. Well, the astronomers were correct. What it amounts to is that almost all stars are red dwarfs. They're just not bright enough to see. But there's like, 100 red dwarfs out there for every star like the sun. So all that red light is being scattered around and gives you this red spectrum, which we see here. So here's the sun spectrum, here's the moon, here's the stars, scaled in magnitude. So that background skylight is like 8 orders of magnitude less bright than the sun. Here's the relative spectrum normalized to the brightest value. So there's the sun. You notice the moon's a little bit redder because it's got these minerals on the surface that absorb some of the blue light, and that shifts the lunar spectrum a little bit to the red. And I hope, Jeremy, that NASA accounts for that when you do your lunar calibrations, but I suspect you guys are aware of that. And then here's the starlight spectrum. So notice overall, there's not much in the blue, and it's just heading upward in the red. Now these lines are what's called air glow, which is emission from the molecules and atoms in the Earth's upper atmosphere. So like this one right here is from oxygen. And so what happens, 300 kilometers up, there's still a little bit of atmosphere. Some ultraviolet light hits an atom, cosmic ray hits an atom, kicks that oxygen up, it drops down, and it emits a photon. So these features are gases in the Earth's far, far upper atmosphere, and then the background starlight is sort of this. So there's that reddish spectrum, and it turns out the astronomers actually know what they're doing. Okay, so that's that.
Do we see that star glow in the solar and lunar spectrum?
Can you see it in what?
Do we see that air glow in the solar and lunar spectrum?
Well, in theory, yes, but in practice, it's like 8 orders of magnitude less, so you just don't notice it. And, okay, so we get out of this guy, and then we'll fire up Hydrolight here, and I'll just walk you through a couple of runs here, show you how things work. So,
Curt,
You got a question, Curt?
yeah,
there's a new product called AccuRT. Are you familiar with it? And
what's it called?
AccuRT.
No, I haven't run into that one.
Maybe I'm saying the name wrong, but it's by Knut Stams.
Oh, okay, yeah, I know him.
I was wondering what the differences are from Hydrolight and the string services.
His code uses discrete ordnance, which is one of these where you have layered things. I think he has a coupled ocean atmosphere code,
Yeah.
and I've never run it, so I don't know how it works. I don't know, does he give it out for free, or how does that work?
He was giving it out for free at the Ocean Optics meeting. I
Okay,
don't know if y'all went to
That's
it.
right, he had a work.
yeah.
Yeah.
It's funny, what John Headley has a simple, actually fairly sophisticated, but simple to run code that he developed himself for work with ESA, European Space Agency. And so he was giving that out for free. This was like 5 years ago. And it was free versus Hydrolight, which cost you $10,000, and nobody would use his code. And so he told me, he talked to a couple of people and said, well, why aren't you using my code? It's free, it gives the same answer as Hydrolight, and what's going on? And people said, well, there's been hundreds of papers published with Hydrolight. If I use Hydrolight in a publication, nobody will ask me anything about it. If I use your code, the reviewers are all gonna say, well, how do you know it gives the right answer, blah, 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 blah. And at that time, he realized that, well, I really want to get Hydrolight, forget the free code. So he approached me and said, hey, can I take over Hydrolight when you retire? So, and there are people like Howard Gordon, for example, that have, and George Cadwar, they have really sophisticated, fully polarized ocean atmosphere coupled radiative transfer models that will put out a better answer than Hydrolight. They're Monte Carlo codes, but they won't give them to you. So it's kind of a weird deal. So I know Stamnus has been working on that code for years and years and years, and I just didn't know that he had some package out that he's giving away, so I'll have to check into it. Have you ever run it?
Yeah,
Okay, does it work okay, easy to use, all of that?
it's not particularly easy to use, and you have to run it in a virtual environment, no
Yeah.
matter what you're running on.
Yeah, and there's an atmospheric code called 6SV that's a vector atmospheric code. And it's free, and I got it, and I gave up trying to run it. It was such a mess to try to install it and run it that I just said, yeah, I don't have time. But I'm sure it works well if you know how to set up the environment and all of this. Okay, anyway, so when you run Hydrolight, first thing you do is cook up what I call the root name that's gonna be used to create file names. So maybe I'll call this Thursday run 1, something like that. And then you can put in some descriptive name like maybe demonstration 1 for Thursday class. Now, in your case, you might have like station 3, you know, latitude, longitude, June, whatever, just to remind you later what went into this run. So anyway, you do that, go to the next thing. Now you're gonna have all these IOP models. And they range from really simple that work at 1 wavelength. There's a couple of models for case 1 water. There's one where you can read in your own AC9 and BB9 and all of that data. There's a couple of models for case 2 water, and there's one where you can build up your own IOP model, which we're not gonna use in here. So let's just pick the very simplest one. This is your first little problem. Here, you know, it says it's just for a single wavelength, homogeneous water, quick and dirty solution. Now, radiant heat transfer people like to just think about 1 wavelength and everything's homogeneous and all of that. So this is for them. So you can put in an absorption coefficient, a scattering coefficient. You can pick a phase function. So let's say we picked Petzold. And then you can put in a wavelength. And this wavelength here is going to be used by the sky model to pick the sky radiance at, in this case, 400 nanometers, which is presumably consistent with these IOPs. So that's the way that one would work. If we back up, let's pick the new case 1 model. There it says, now we're gonna build up the total IOPs from pure water and then chlorophyll-bearing particles and co-bearing CDOM and non-algal particles. And all the IOPs are determined by the chlorophyll concentration. So if we go to that guy, and there's various ways you can pick pure water. You can let the water absorption and scattering coefficients be determined by temperature and salinity. That's the default. And then you can use various databases that people have developed for seawater and freshwater and older ones that people used to use. Or if you've measured your own pure water absorption and scattering coefficients as a function of wavelength and you think they're better than these, fine. You put them on a data file, you can click here, go browse and read your data. Okay, so let's just take the defaults. And then, of course, Hydrolight already knows what the phase function for pure water is. And then you can put in the chlorophyll. So maybe you decide that the Damascotta River we measured and it was 3.2 milligrams per cubic meter, you can stick that in. If you have a file where you've measured the chlorophyll data, you can put that on a file and browse for that. And we'll see what those files look like this afternoon. So for the moment, let's just stick that value in and assume that the water's well mixed, so this is constant with depth, which is probably reasonable for the Damascotta River. There's some options here on how to handle chlorophyll absorption in the UV. We'll just take the defaults, but what's going on there is if you look at chlorophyll or phytoplankton absorption, here's 400, 300. Well, you get this sort of curve you've all seen now out to say 700. So that's coming out of your AC9. But if you actually measure phytoplankton absorption down to 400 can look like that, it can look like that, it can look really huge. And this behavior here is due to what's called mycosporin-like amino acids, which can literally give you like a factor of 50 difference in the phytoplankton absorption from, let's say, summer to winter. So I've built in, from the literature, 3 different options here for how to extend from like sort of 350 down to 300. We could just use the medium one here if you want, and just go with that. Okay, so in this case, it doesn't ask us for a phase function because that's being determined by the chlorophyll concentration with these equations that are described in here that were cooked up by Andre Morel and his co-workers. Okay, so we've now specified the IOPs. We can do things like include chlorophyll fluorescence, CDOM fluorescence, Raman scattering, or if you don't want to include it, uncheck the box. So if you want to see something like, how important is Raman scattering in my water? Well, you do one run with Raman scattering and one run without and see what the difference is. That's this controlled environment business. A little warning there. Let's say you're only interested in 400 to 700 nanometers and you want to include Raman scattering. Well, where's the light, the Raman scattered light at 400? Where did that actually come from?
350?
Yeah, somewhere down around 350 or 360. So you actually want to start the run at maybe 350 so that the light here that's Raman scattered over to 400 will be there, even though you don't care about 350, you just want to have it from 400 on. If you start the run at 400, the run without Raman might look like that, and then the run with Raman will look like that. And you'll actually see where the Raman from 400 starts appearing at somewhere around 450. So there's little things like that that you just get used to doing, but they're a little weird at first, like, well, why did I have this little kink here? Well, it's because I should have started it back here. Okay, so let's say we include those things, and you know, it has a little window that says, okay, chlorophyll's coming from here, CDOM I'm going to get from the chlorophyll, and then the run must include the relevant excitation and emission wavelengths. So that's what I'm talking about here. And you know, I've had people, all they're interested in is the chlorophyll fluorescence line height, and they do a 1 wavelength run out here, and they don't get anything. Well, that's because this fluorescent light came from all the way back here. And then they say, oh, I get it now. So anyway, then here, notice there's no option to do a run at just 1 wavelength. How come? Louder?
Because the excitation emission.
Yeah, because I checked the boxes back here that said include inelastic scatter. Well, you can't do that if there's just 1 wavelength. If I uncheck those boxes, now if I want to do a run at just 1 wavelength, I can. Okay, so let's just pick, let's say we want to do a run from 400 to 700 by 10 nanometers, fine, we can put that. If you have particular wavelength, like you have an instrument and it's measuring from 437 to 444 nanometers, you know, you can put in a list and include those 2 boundaries to make sure the output corresponds to exactly your instrument. But for the moment, let's just go with that. You have to put in the wind speed. That's going to determine the reflectance properties of the surface. You can either put in an index of refraction for the air water or for the water, or you can let it be determined by the salinity and temperature. There's a couple of sky models. The one that's normally used, it says semi-empirical model based on RADTRAN. RADTRAN is an atmospheric radiative transfer code that gives you spectral irradiances onto the water, and then there's another code that takes those and turns them into a radiance distribution. And that's what you will normally use for runs. There's also an option here for an idealized sky model. So if you wanted to study like a sun in a black sky or a uniform sky or something, you can run that code. And here, it's not letting you pick it because we're doing multiple wavelengths. And this guy is going to give you the same sky at every wavelength. So that's why we're using this guy. In Hydrolight, it's the X direction is always downwind. That has, yeah, Mortimer.
I just want to ask something actually from before regarding wind speed.
Okay, hang on.
No, it's on that one. It's on that one.
Okay,
You said the physical model does not include whitecaps.
yeah.
So how sensible is it then to include or increase the wind speeds?
Well, here's the catch. So the Cox-Monks equations, you can put in any wind speed you want. The data that were used to develop those equations was sort of like, 5 or 10 meter per second winds. So the water at that time did not have whitecaps on it, or negligible. Now, if you put in a 50 meter per second wind, Cox-Monk will give you some answer, but you kind of know it's wrong because the sea surface would just be totally covered with foam. So it's not a good thing to do. Then NASA cleverly gets around this by saying, well, if the wind speed's more than 15 meters a second or so, we assume it's in a hurricane and we can't do remote sensing anyway, so we don't care. Is that a reasonable statement of reality there?
Yep.
Yeah.
Okay. So keeping it at 5 is actually.
Yeah, so I sort of say, when you run Hydrolight, go somewhere between 0 and 15 meters a second. And now there is, in the full-blown version, you get sea surfaces that were created using wave variance spectra and Fourier transforms and all of this, and it makes surprisingly little difference. But if you wanted to put in a hurricane, you could do it that way, although the database currently, I think, only goes up to 15 meters a second. Okay, so anyway, this azimuthal angle really won't matter in here because we're using azimuthally averaged surface reflectances from Cox-Monk. In the full-blown code where you can have the surface reflectance being different in the along wind and crosswind directions. Then if you want to put the sun downwind at 0, if you wanted to put the sun at right angles to the wind speed, put in 90 degrees, and it'll make a little bit of difference in some things, but not a whole lot. Okay, so you can just use that and go with it. Okay, what does matter, of course, is the solar zenith angle, so you can either put in an angle, or if you want to match up with your cruise yesterday, you can put in, you can browse for the date, the latitude, the longitude, etc., and Hydrolight will figure out where the sun was, but it doesn't matter anyway, because as I understand it, it was cloudy yesterday, so you couldn't see the sun anyway. So for the moment, we'll just use that. You can put in 0 is a clear sky, 100% is 100% solid overcast. So for out there today, you can stick in 100 there and you'll get this sort of overcast sky. Okay, we'll just go with that and we'll just pick the default rad trend there. If you actually had measured, like on the ship, if you had a cell to measure the ED sky irradiance above the surface, put it on a data file. You can read it in here in various ways, but for the moment we'll just compute it from the sun angle. Okay, then you get to tell it, is the water infinitely deep or finite depth? If it's finite, you need to tell it how deep it is and what the bottom reflectance is. So there's little built-in databases here for average seagrass, average coral, average wood, sand, etc. You could pick one of those, or you could let it be a gray bottom independent of wavelength, or you can let it be infinitely deep water. So that specifies the bottom, and then the final thing is how deep do you want to run the code and what depths do you want to save the output at? So let's say we want to do a run down to 20 meters and we want to save the output every 5 meters. Now, if I had picked the finite depth bottom, it would put the bottom at 20 meters. As it is, it'll let this be the last depth where it computes the output. And so a thing to worry about is this. Here's depth, and here's IOPs. Now, if the water's homogeneous, so here's the absorption coefficient, and it's this value all the way down, and you go down to 20 meters. Well, it's actually gonna solve the radiative transfer equation down to 20 meters, and then it fixes up a bottom boundary condition that just says, use this value from there on down, and it does the math correctly, and you get what's the solution for an infinitely deep water column. Suppose you have this profile of IOPs, and you say, solve to 20 meters. It'll use your profile down to 20, and then it'll take the value at 20 and say, just use that from there on down. So, that's not really the problem you wanted. If all you're interested in is remote sensing reflectance, it's not getting any light from below 20 meters anyway, probably, so that's fine, you won't see any difference. On the other hand, if this were, maybe 5 meters, and you just wanted remote sensing reflectance, well now, water down at 10 meters, say, some of that light's getting back out and helping determine the remote sensing reflectance. So you want to go to some depth, let's say it might be 20 meters down here, so you solve the radiative transfer equation with this profile and then this value from there on down. So you're solving, in one case, you're solving this IOP profile, and in the other case, you're solving the red one. And if you wanted to look at the light field, at 5 meters, you better use this one or you'll get the wrong answer, because this is a perfectly good radiative transfer problem. It's just not the one that you were interested in. Okay,
Curt,
yeah,
if you're just trying to derive the water leaving radiance, but you have a stratified water column or something really,
right.
how do you maximize?
Then
how
what you can
deep to
do
go?
is just run down to say 50 centimeters, half a meter. And it'll say, okay, solve the equation here, use this value on down, it's homogeneous, you get exactly the same answer as if you run it down here, it'll just be much faster. And that only works if it's homogeneous water without inelastic scattering.
But I was asking if it's not homogeneous water and you want to maximize just, having an efficient runtime.
Sort of like how do you decide how deep to go?
Exactly.
You just, it depends on the IOPs, the sun angle, etc. And usually what you have to do is you do a couple of runs, maybe a really deep one, it takes a long time, then you back up, say, well, it didn't make any difference. Then you back up, oh, now it made a difference, so I better go to this depth.
Okay.
But there's no easy rule of thumb there. If you remember, I mentioned that what Howard Gordon calls the penetration depth at a given wavelength is something like 2 over KD at that wavelength. So if you knew KD, and let's say the water was clearest at 550, you could look what's KD at 550, and let's say it was 0.1 per meter. Well, 0.1, that would say you're seeing the bottom down to about 20 meters. So, or you're seeing into the water column around 20 meters. So you ought to run Hydrolight to 20 meters.
Right.
But of course, if you knew KD, you probably wouldn't be running Hydrolight anyway, because that's one of its outputs. So it's just kind of trial and error, and when in doubt, go a little too deep.
Thanks.
Okay, usually, if you're doing like 100 runs, you've got some water IOPs, you want to do like different sun angles or something, You do a couple of runs, figure out how deep to go, and then you can crank through the rest of the runs at that depth. Okay, so there's output options. You always create the standard printout. We'll take a look at that in a minute. There's a couple of options for creating Excel spreadsheets. I tend not to use Excel because I consider it to be untrustworthy, and the graphics I can do better with a pencil and paper. But anyway, we'll go ahead and create them. There's digital files that are written, and I have IDL programs that I read those in to do my post analysis. And there's it's called the L file, the radiance file. It's just a big file. It has depth, theta, phi, wavelength, and radiance is all in a big file if you want to look at that. So we'll go ahead and create it. And now we've gone through the user interface, so you can click there and save all of this stuff we entered, and that becomes the default for the next run. So then you can just click, 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 change the sun angle, whatever, and do another run. You can also now click here and go back and enter a second run and third run and just stack these up, and then click the button. It'll run them one after the other when you go to lunch or something. So let's go ahead and just run this guy. So it's now spun off this window. It's piped our little input file off to Hydrolight, and away it goes. And this will take a minute or two to run. So you can see it's sort of taking a second and a half per wavelength to solve down to the 20 meters or whatever it was I had here. And now if you run it out to beyond 700 especially, it'll start getting really, really slow at each wavelength. So why is that?
If you go out beyond 700 nanometers, it gets really slow. Why does it get really slow?
Yeah, so here it was taken, you know, it finally got up to 2.2 seconds at 695. But if you went to 1,000 nanometers, this would probably be like 20 or 30 seconds. It's because of the pure water absorption. So remember that if we plot absorption versus wavelength, okay, so here we are down in the blue, 400, 700, and then out to 1,000. Now, once you get past 700, the water absorption goes way up, and there's no way to get around that. The water's always there. So if you go to, let's say, 50 meters here, that might be 2 optical depths, but 50 meters over here might be like 30 optical depths. So the runtime depends on the optical depth at that wavelength. So out here, this is going to take 15 times longer to run than it does here, just because of the water IOPs. So be forewarned. Okay, we're done with that. Let's just run Hydrolight. Same inputs exactly, and see, it's going at like 1/10 of a second, and boom, it's over. So now to look at output. When you go to whatever directory where you have the code installed here, here we are. Okay, so there should be a directory called output, and then there's Hydrolight and Hydrolight, and then each one of those has a digital, an Excel, and a printout directory. So and there's the run we did. It took the little root name was Thursday, run 1, and there's the printout file. So if you look at this, what's in there is just basically a big listing of all the inputs. You know, it tells you, here's the IOP model, blah, 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 got pure water values, etc. Chlorophyll was constant with the depth, you know, so on and so on. There's the chlorophyll profile. There's how it got the CDOM absorption, and so on and so on. So it just documents, here inelastic was not included. Here's the input for the atmospheric model. So when you come back, you get some really weird looking result that doesn't make sense. You look in here and you realize, oh, well, I typed in 0.3 for the chlorophyll instead of 3. So that's just to document what's there. And then finally, you get down to, and here it says, begin warning message for input data files, and it didn't find any problems there. Another thing that will generate a warning message is this. So here's A and wavelength, and let's say this is 350, 400, on out to 700, 750. So you have an AC9. The first wavelength is at 412, then you got one at 443, and then finally one out here at 715. So when Hydrolight runs and it says, well, I'm at this wavelength here, I need to know the IOPs. It will take your measured values and interpolate between this value and this value to get what it needs. But you started the run at, say, 350, and you read in AC9 data. Then Hydrolight says, I don't know what the IOPs are back there. So what it does is it takes the nearest value and just uses that as though it were constant. That's probably not right. If you started at 400, that's maybe okay. If you went back to 350 or 300, that's undoubtedly going to be wrong, because really the absorption went like this, or it went like that or something. So there will be a message here that says, hey, your data didn't cover the range of the run. You need to think about whether you want to trust the output. And out here, it'll take this value on out. And if your data started, here's depth and IOPs, and your data started here, it'll take these values and interpolate to get what it needs at this depth, but it'll take this value here up to the surface and this value here from on down. So you get little messages like that. If something like that happens, and you can then think about, this is probably okay, I might be okay with that, but not with that. So, or if there's something horrible like it read in a negative absorption, it'll have a message here that says, this depth and wavelength had a negative absorption, I set it to 0 and continued, you need to clean up your data. So just kind of look through, see what's going on there, if anything. Then, if we look further down, okay, there's tables of the IOPs and such. And then finally, here we now get to a table where here are the output. It says spectral irradiances, the units. So here's the ED, here's EU, the value in the air, so just above the surface. Depth 0 is in the water just below the surface, and we told it to run to 20 meters and save the output every 5 meters. So here's our profile of ED and scalar irradiance. We talked briefly about the mean cosines and such. So there they are. There's the irradiance, reflectance, and so on. And then there's a table of radiances in various directions. So here's LU, LD, horizontal looking towards right angles and away from the sun, and then various other things. So here's the remote sensing reflectance at that wavelength. Here's the water leaving radiance. Now the value over here, the L total, LU, that's the total. So that's water leaving radiance plus surface reflected. So there's that kind of stuff. There's other tables of radiances that the remote sensing people want to see. There's K functions. And then you do the same thing at the next wavelength. And so then, if you finally go down to the bottom, after it's done all the wavelengths, Okay, so then there's tables of band integrated irradiances. Now, remember, Hydrolight is outputting spectral values, so per nanometer. Then these values have been integrated over the bandwidths. So like these, in this case, was 10 nanometer bandwidths. So this is the band integrated as watts per square meter, not watts per square meter per steradian. And so then here's the energy units, here's the quantum units, micromole photons per square meter per second. These are the things that go into computing PAR. And so here's table of PAR, computed correctly from scalar irradiance, computed from ED. Notice there's, 30–40% difference there. So that's why